right, welcome to the 2018 FRQs. We're going to do numbers 4 through 6 on this video. So starting, and these are all non-calculator active, so no calculator allowed. Number 4, the height of a tree at time t is given by a differentiable, twice differentiable function h, where h is measured in meters and t is measured in years. And selected values of h of t are given in the table above. Keep in mind, h of t is your output. Part A, we want to use this to evaluate h prime of 6. H prime of 6. Okay, so, and then using correct units, we want to interpret the meaning of h prime of 6. So if I look, you might notice 6 is not one of the inputs given on the table. So what I'm going to do is I'm going to use the two inputs that are bracketing inputs of 6, and I'm going to use them in order to do this problem, this estimation. So h prime of 6 could be estimated by using h of 7 minus h of 5 over 7 minus 5. So I'm going to use slope to estimate this rate of change. So this would be 11 minus 6 over 7 minus 5, which ends up being, let's see, 5 over 2, or 5 halves. Now I do have to include the units on this one as well. I will mention that you can leave your work like this. You do not actually have to simplify it. As long as there's no functional notation or variables left in the problem, you can actually leave it just like that. And so if this were an actual AP exam, you might want to do that, because every time that you compute something, you're taking a risk that you have computed it improperly. So in terms of units, h has the units of meters, and t has the units of years. And so when we're doing h prime, we're doing a rate of change. And if you just kind of notice, like in our slope, we've done h over t. So our units would match that. So our units would be meters per year. So it should match what you did here with your slope. We also have to interpret the meaning of this. So what this is this is the approximate rate of change. And we have to say, of what is it a rate of change of? Well, it's of h. So rate of change of h, which is the height of the tree. So it's the approximate rate of change of the height of the tree in meters per year. You could abbreviate meters if you want. And you have to say at what interval that you're doing this of, or what instant. We're approximating h prime of 6. So it's approximating the rate of change of the height at t equals 6 years. A lot of students won't put this part, and so they will miss some of the points for the actual guideline because of the fact that they don't have that in there. And so that is something that you want to pay attention to, is that really does need to be part of the response. Okay, part B. Explain why there must be at least one time over the interval from 2 to 10, open interval, the h prime of t is equal to 2. Well, anytime that you see something that says like at least one time, that's probably using one of our theorems. And the goal would be to say, well, which theorem? Which theorem? We're talking about, we're looking here at h, and here they're talking about h prime. So we're looking at a rate of change. We're looking at a derivative equaling a specific value. This is using the MVT. They want us to use the MVT. Now, what the MVT says is that if a function is continuous and differentiable, then, okay, so the MVT does have a requirement that it has to be continuous and differentiable. And if we look at h, we know that h is. And I'm going to mention that condition. H of t is, we know it's differentiable, and thus it is continuous. That's important to state. You cannot use the MVT until you've listed, how do you spell continuous? Continuous, there we go. Until you've listed its conditions, so don't even try. Okay, that'll be really important. They just stop grading there if you don't have that listed. Now I want to see, can I get this? 2, what the MVT is that the derivative would equal the slope somewhere in the interval. So now they specifically said from 2 to 10 for our interval. Okay, now the MVT applies, it's on an open interval for where the derivative is, but we can use those endpoints. But if I check this would be 13.5 over 8. That's not 2. That doesn't mean the MVT doesn't apply. It means I need to see if there's perhaps a different interval that would give me a slope of 2. So if I kind of keep looking, you might eventually land on this one. If you compare those two, I'd have 4 over 2 for the slope. Those are the ones I'm going to use. So I'm going to say on the interval from 3 to 5, which is in the interval from 2 to 10, okay, for t, we can say that h of 5 minus h of 3 over 5 minus 3 is 6 minus 2 over 5 minus 3, which is going to reduce down to 2. Now, I do want to show that on here. I at least, again, need at least this, and I should at least verify that that would equal 2, even if I don't show the work. So by the MVT, and I'm just going to restate the question. There exists at least one time where h prime of t is equal to 2. So, is equal to 2. So the things that you must have in order to get all the points, you must have the conditions met, differentiable and continuous. We need to have an interval listed that is going or shown. It can also be shown in here, but you should be somewhere saying that this is inside that interval of 210, where we have that slope that would equal 2. You must name the theorem, and then restating it is always a really good idea. All right, part C. We want to use a trapezoidal sum with the first 4 subintervals indicated by the data to approximate the average height of the tree over the interval from 2 to 10. By the way, make sure you always check the interval, because this table goes from 2 to 10, but sometimes they ask you to do a Riemann sum that's not from 2 to 10. Maybe it's from 3 to 7. So make sure you look, because they may not actually ask you to do it all the way through the entire interval. So this is a perfect example of one where you don't want to simplify. I would never actually simplify this one. I'm just going to write it all out. But there's one thing that students miss. They miss the average height. Average height, this is the idea of 1 over b minus a times the definite integral from a to b of whatever it is you're measuring, which in this case is the height. Well, we're not going to be able to do the definite integral with an expression. That's why we're approximating. We're going to approximate this portion, the definite integral portion, with the Riemann sum. But I need to still do the 1 over b minus a out front. So I'm going to do 1 over, let me change that font. So I'm going to do, for part C, 1 over b minus a, and then times the trapezoidal rule. Now, the trapezoidal rule, you have a 1/2 times the height, which in this case is really looking more like the width of each interval, and then times the sum of the two, the sum of the two different, in this case, heights, okay, or the bases of your trapezoid. So I'm going to factor out the 1/2 because all my trapezoids are going to have a 1/2, and then I'm going to include the rest of it inside here. You could also choose to keep your trapezoids each with the 1/2 as a multiplier. It's up to you, it doesn't matter. But our trapezoids start and end at the same place. So just keep that in mind, okay? The width of the first trapezoid, if I do 3 minus 2, is 1. The width of the next one's 2, and then 2, and then 3. So I want to do that width, because these are on their side. So normally in the formula for a trapezoid, this is height, but here it's more like the width of each of these times the sum of the two bases, which are actually the heights, plus the width of the next one, which is 2, times the sum of their two heights, plus, looks like I'm going to need more room, the width of the next one, which is also 2, times the sum of the two heights belonging for that trapezoid, plus the width of the next one times the sum of the two heights. And I would not touch it. from there, I would absolutely leave it. This ends up equaling, I don't know, like 263 over 32. Imagine how much time it could take to get to that. Just leave it like that. There's no reason for you to spend your time. You're likely to spend a lot of time and unlikely to get there without any potential problems. So I would just leave that. All right, part D. The height of the tree can also be modeled by this function g. Oh, that's weird. Okay, and g, notice, has an x. Our input for h was t, and now all of a sudden they have an x. This is x is the diameter of the base of the tree in meters. So that's different. Okay, that's something that's unusual. When the tree is 50 meters tall, the diameter of the base is changing. It's increasing at a rate of 0.03, let's see, meters per year. So as the tree grows, its diameter gets bigger. According to this model, what is the rate of change of the height of the tree with respect to time in meters per year at the time when the tree is 50 meters tall? All right, well, let's see if we can break this down a little bit. So for part D, the height of the tree can be given by g of x. And I'm just going to make sure that I know that that's the height. And remember, x is the diameter for my input of the tree. When the tree is 50 meters tall, so when the height is 50, the diameter is increasing at a certain rate. And so that's kind of an interesting idea. So when g of x is equal to 50, the rate of change of the diameter, remember x is the diameter, is increasing at a rate of 0.03 meters per year. This is with respect to time. We don't even have time in our equation, so that's really interesting. Okay, so that's a surprising thing. Now, according to this model, what we want to find is the rate of change of the height. So we want to find dg with respect to time. Notice we don't even have time in this equation. This equation is in terms of x. And we want it specifically when g is 50. Okay, so we want that to happen there. Well, we can tell we want a derivative of h, but if I take a derivative right now, or a derivative of g, find the rate, oh, I wrote this weird. Find the rate of change of g. There we go. That's better, with respect to t. So I want to find the derivative of g, but with respect to time, not with respect to x. And currently, this is written with respect to x. This is a problem that's being done implicitly. X is my wrong variable. I want t to be my variable. So if I want to find this, I'm going to take the derivative of this expression. If I want to find this, I'm going to take the derivative of this expression here, and I'm going to have to use the quotient rule to do it. So the quotient rule would be the denominator times the derivative of the numerator, but I'm doing this with respect to t, not x. So I have to multiply this by dx over dt minus the numerator times the derivative of the denominator. But anytime I take a derivative that involves x, I have to do times dx over dt. And then all divided by the denominator squared. Now I want this specifically to be evaluated when g is equal to 50. When g of x is equal to 50. But notice, g is not in my equation. These are x values. So what I'm going to need to do is I'm going to do a little side work. The formula for g of x is 100x over 1 plus x, and I'm going to set that equal to 50. I need to find out what x is. I'm just going to cross multiply this. So 50 plus 50x is equal to 100x. So 50x is 50 and x is 1. So I want to actually find this when x is 1. And so now I'm going to go back through here. Wherever it says x, I'm going to substitute in a 1. Wherever it says dx over dt, I'm going to substitute in a 0.03. So this is 1 plus 1 times 100 times 0.03 minus 100, optional if you want to write times 1, that's up to you, times 0.03 over 1 plus 1 quantity squared. I would not simplify this. Now, I am going to mention the units because related rates problems do have units in them, and so it's a good idea to mention this. So they kind of told me here it's the height of the tree, which is meters, with respect to time, and time they had mentioned earlier in the problem is years. I would leave it like this. I would not simplify this. This ends up simplifying to 3/4, but is not worth your time. So I would not do that, and I also would not risk potentially having the wrong work for simplifying. I'm going to just really quickly pull up the scoring guideline for this. All right, so here are the scoring guidelines. We'll just kind of compare. So we have the correct estimate for part A. And if we look at the interpretation with units, we have the correct interpretation at years. Notice it mentions specifically at 6 years. So we would get 2 out of 2. For part B, we do have the correct interval and slope to show 2. We have mentioned the conditions. We mentioned the MVT and restated the question. So we would get 2 out of 2. On this next one, we have the actual trapezoidal sum. We did not bother to calculate it, which is totally fine. And we have, so that's this part. And we have the average value listed, which you could simplify or not. That's 2 out of 2. And then part D, we do have, let's see, they want 2 for the quotient rule. 2 for the quotient rule. Now, I was AP reader in the year that we did this, so I can tell you that they gave 1 point for this part of the quotient rule and 1 point for this. Now, we did ours a little differently. We put that dx dt inside each time we did that. They kind of factored it out. It's fine the way that we did it. It works. You do get those 2 points and 1 point for the answer, which does not have to be simplified. So what we wrote was fine, 3 out of 3. So that's 9 out of 9. Freaking out here. Let's see if I can fix that. There we go. Let's take a look at number 5. All right, we want to look at the function f, and it's defined by the expression e of x times the cosine of x. First, we want to find the average rate of change. There's a difference between average value and average rate of change. Rate of change is slope. We want to find the slope. So we need to calculate f of 0 and f of pi, and then we will use slope between those. So if we calculate f of 0, that's e to the power of 0 times the cosine of 0, which is 1 times 1, which is 1. F of pi would be e of pi times the cosine of pi. Well, the cosine of pi is -1, so this is negative e to the power of pi. If I then do the slope with this, I would have negative e to the power of pi minus 1 over pi minus 0. You could leave it like that. You could also have these with the exact opposite signs if you'd like. Oops. Part B, we want to find the slope of the tangent line specifically when x is equal to 3 pi over 2. Well, this is asking us to find f prime of x and then to evaluate f prime of x at 3 pi over 2. I'm going to need to use the product rule in order to do this. So I'll do the first times the derivative of the second plus the second times the derivative of the first. There's my actual power rule. And then I will evaluate this at 3 pi over 2. It's going to look ugly. I'll pull this negative out front. So negative e to the power of 3 pi over 2, I'll leave that, times the sine of 3 pi over 2 plus the cosine of 3 pi over 2 times e to the power of 3 pi over 2. Well, the sine of 3 pi over 2 is -1. Times this -1, this would be e to the power of 3 pi over 2. And then this is 0 times all of that, so that will 0 out. So for part B, it'll be e to the power of 3 pi over 2.